All right, let's get right into it. For a long, long time, the blueprint for a computer chip was, well, just a blueprint, a static map. But what if I told you that at the ridiculously small scale of today's chips, that map has basically come alive? That the actual arrangement of the transistors fundamentally changes how they work?
Just let that sink in for a second. What if the speed of a single tiny switch on a chip wasn't just about its own design, but about what other little structures were sitting right next to it? I mean, that sounds like complete chaos, right?
Well, it turns out it's not chaos. It's just physics. Once you get down to the 7 nanometer scale, this isn't science fiction anymore. It's the day-to-day reality of chip design. So, welcome to the wild and fascinating world of what we call local layout effects, or LLEs for short.
So how in the world did we get here? To really get it, we've got to talk about why the good old days of designing chips are, well, they're over. The era that engineers lovingly called happy scaling has officially ended.
For decades, the playbook was incredibly simple. Just shrink everything. This was called Dennard scaling, and it was awesome. Every time you made things smaller, you automatically got more performance, you used less power, and the chip got smaller. It was a total win-win-win. But then, around the 2010s, we hit a brick wall. The free lunch was over. Today, we're in the DTCO era. That means you can't just shrink your way to success anymore. You have to get incredibly clever, co-optimizing the chip's design with the technology used to build it. And that means you have to wrestle with some seriously tricky physics.
Okay, so if just shrinking stuff doesn't work anymore, what do you do to get more speed? Well, this is where it gets really cool. One of the most brilliant tricks in the book is to literally squeeze and stretch the silicon atoms themselves. Yeah, you heard me right. We're engineering with pure force.
The fancy term for this is strain engineering, and all it really means is that we're intentionally using mechanical stress to physically warp the transistor's channel. This actually changes the crystal structure of the silicon, creating a kind of superhighway for electricity to flow through. And faster flow means, you guessed it, a faster transistor.
A key example of this in action is with the specific type of transistor called a PMOS device. For these, engineers grow a material called silicon germanium, or just SiGe, right next to the channel. Now, SiGe's atomic structure is naturally a bit bigger than silicon's, so it literally squeezes the silicon next to it. It creates this powerful compressive stress that acts like a turbocharger for the PMOS device's performance.
But, and this is so important, there's a huge catch. This squeezing force is a double-edged sword. For those PMOS transistors we just talked about, it's fantastic, a massive performance boost. But for the other kind of transistor, the NMOS, that same exact force is a total party pooper. It actually degrades performance and slows them down. So remember this, squeezing PMOS is good. Squeezing NMOS is bad. That's the key.
And this is where we get to the heart of the problem. You have these engineers who have carefully designed this perfect amount of stress to make the PMOS devices fly, but it turns out there are these little saboteurs hiding in plain sight in the chip's layout, and they're messing everything up.
So let's meet our two main suspects. They're called diffusion breaks and gate cuts. And you can't just get rid of them. They are absolutely essential. Think of diffusion breaks as tiny fences to keep different active parts of the chip from interfering with each other. And gate cuts? They're basically the stop signs at the end of a row of transistors. You have to have them.
And here's the kicker. Just by being there, these totally necessary structures mess with the physics. They change the mechanical environment around the transistors. And that beautifully engineered stress we worked so hard to create, it gets all distorted. The result is just unpredictable performance that can vary like crazy from one transistor to the next.
You know, the tiny details of how you actually build the chip matter a lot. And the specific technology we're looking at today uses a process called a gate cut first integration. All that means is that those gate cuts are put in place pretty early in the manufacturing process. And that choice has a huge impact on exactly how these stress effects play out.
Right. So you might be thinking, is this all just theory and computer models? No way. This is where we look at the cold, hard data from actual, physical silicon chips. And that's what shows us just how big of a deal this really is.
We're not talking about some old, outdated tech here. This is the absolute cutting edge. All this research is based on a real-world, commercial 7-nanometer FinFET process. That's the 3D transistor architecture at the heart of pretty much every modern chip you can buy. And to make sure this wasn't just some random fluke, the scale of this study was just massive. We are talking about electrical tests on over 30,000 individual transistors. This is some serious, statistically robust work. So what did they find? Get this. Just by changing the position of those neighboring isolation structures, the performance of a PMOS device could swing by more than 10%. In the world of chip design, an unpredictable 10% variation is, well, it's a nightmare.
And don't just take my word for it. Look at the proof right here. This chart tells the whole story. The blue dots, that's the real data from thousands of tests on actual silicon. You can clearly see that as a gate cup gets closer, performance drops. Now, check out those open red circles. That's the computer simulation, the TCAD model. I mean, look at that match. It's fantastic. This is the smoking gun. It proves the effect is real, it's measurable, and most importantly, it's now predictable.
So what's the big picture? Why does this matter to the companies that are actually building these chips? It's simple. When you're running a multi-billion-dollar fabrication plant, the last thing you want is randomness. Chaos is your worst enemy. The name of the game is predictability.
And that's exactly what this research delivers. It's a roadmap. You start by measuring the effects on real silicon thousands of times. You use that data to build and fine-tune incredibly accurate physics models. Then, you distill all that complex physics into simpler, efficient models that designers can actually use. All of that gets bundled into what's called a process design kit, or a PDK, that is now LLE aware. And that is what enables true design technology co-optimization, so we can all get better, faster, and more reliable chips.
So the most crucial point here is this. You're never going to eliminate these physics effects. They are baked into the very fabric of the nanoscale. The goal isn't to fight them, it's to understand them and predict them so perfectly that they can be managed and even accounted for during the design process.
And that brings us full circle, right back to the core idea of all this research. It represents a fundamental shift in how we have to think. For chip designers, the layout is no longer just a drawing. It is an active, physical component that is part of the device physics itself. And mastering that connection, that's the future of semiconductor engineering.